Alright. So what are the initial questions for either the heap module or any other module if we want to get into that? Probably make more sense to go over some of the new heap challenges first, but I'm open to answering questions on anything this office hours. Okay. So you are interested in Toddler 6 and Toddler 7. Let me try to launch that. You said you wanted, sorry, you said you just want to look at 7 or you want to look at 6 and 7? I think that is technically true, yes. Okay, let's start by briefly talking about 7 and then we'll jump back to heap because I'm also seeing questions about heap. But I will definitely at least give a quick overview of 7. And then if you have more questions, you can either ask later on in office hours or message me on Discord. Okay, let me launch 7 then. Level 7. Okay. So if we launch it, we can immediately see, of course, that it is a Yawn 85 style challenge. Let's see here. So custom emulator, blah blah blah, and we get to send it code. Okay. Let me think about what to say to be brief without also just immediately giving the answer on level 7. So as you reverse engineer level 7, actually let me see if I can pull it up in Binary Ninja. Maybe that will be the best way to look at it. And that. And we add window capture. Actually, no, that's not right. Oh, there we go. Okay. Window capture, and we want to capture Binary Ninja. Okay. And let me resize this. Alright. Verify on Twitch so you can see it. Yep, okay. So this is Binary Ninja for Toddler level 7. So I guess the first thing to do when not working on a completely brand new challenge, but a challenge based off of previous challenges, as is the case for these Yawn 85 challenges. Hopefully you're at least a little bit familiar with how the Yawn 85 architecture works and what some of the things are that are going on with this. So the immediate thing that we'd probably be thinking of is how to do our Yawn 85 exploit, where our or not exploit, but we get to input code. So the immediate thing you should, of course, think in your mind is, all right, well, let's just we have some syscalls in Yawn 85. We have a syscall to open a file. We have a syscall to read into memory from that file, or maybe that's not the right verbiage. Let's see quickly what our syscalls are. If we look at interpret sys, we have the ability to, and since we're in the teaching, we can just kind of look at the string to see what it does. We have the ability to open a file, and of course, with all of these, you might want to look into the very specific details, but for now, I think we're just interested in the high-level overview. We have the ability to read into memory. This is, oh, does it just go down? Okay. Actually, we can see right here also that this syscall seems like something may have changed. I don't think this is how it always is. We can see that there's this disallow. Let me actually zoom in a bit. Trying to see how it looks on Twitch. Yeah, that looks better. Okay. We have this thing that will eventually call crash, which I presumably just ends the program or whatever, with this disallowed system call. I thought you could double click on this. It turns out that this says sys underscore read underscore code, because this one is for reading into memory, which is not actually blocked. But anyways, so we have the ability to read some data into memory. We have the ability to write from memory. We have the ability to sleep. The ability to exit. And am I missing anything? Sleep, write, read. Open. Okay. So normally what we would do is, actually, hold on, kind of need to refamiliarize myself with what's going on here. Oh, I see. Because I'm looking at 7 instead of 6. That's why I'm confused. Okay. So as it turns out in 6, which is not what we're looking at 7. In 6, the open syscall is actually blocked. So in 6, the thing stopping us from just going and doing open and then read the flag in and write it out is that in 6, open is actually blocked. So you can't just go ahead and do that. And then the other thing is, let me familiarize myself again. So that is with 6, you can't call open. And then it's also the case that in both actually 6 and 7, if we, where would we look? Maybe main. Let's see if this will look good for us. Oops. There's this assertion right here that the, where is that? Why does it feel like this control flow is missing in the high level IL? Oh, it's right here, isn't it? for if it's less than or equal to 1, right? Okay, so what this is doing here, which of course, just for brevity's sake, we're just going to kind of quickly get into what it's doing, is that it's basically counting the number of syscalls that are in your YON85 code. And it's verifying that there is only, or it's counting the number of syscalls. So this var 420 is the number of syscalls present in the code that you pass to it. And then if it is less than or equal to 1, it'll enter the interpreter loop. And we can see that there's a no return after here. So I guess Binary Ninja, this is kind of like an else statement because there's a no return here. So if we do execute our interpreter loop, we don't have to worry about this assertion fail. And even if we did, it would happen after the fact, doesn't really matter. But moral of the story is that if this isn't the case, if this number, if we have more than one syscall, we will assert fail out rather than interpret it. So what this means is that we are only allowed to have one syscall. So going back to our immediate instinct of what we'd want to do on this challenge, which would be to kind of open the flag, read it in, write it out using YON85 instructions, we're not going to be able to do that because we're only allowed one syscall. So how can you do that with just one syscall? Now there are, of course, this is still solvable, even if we can't do our traditional our traditional code. And something to, I guess for brevity's sake, something to realize is that in level 6, there is some potential memory corruption options. So basically, if you're interested in looking for memory corruption options, basically what you want to always keep in mind is how does your input flow into the system? It's kind of the main way to think about memory corruption, or really most exploitation. You really want to think about how can I interact with this program in a way that influences it, right? That, I mean, maybe that sounds kind of dumb or whatever, but that's kind of the starting point for all exploitation and interacting with a program is what can I do to influence it? And specifically in the case of memory corruption, you're interested in exactly where your input is coming in. So you're interested whenever the program uses basically a read syscall, whenever it's taking in your user data. Of course, there's other ways for you to influence the program and input data, but for like a basic or a buffer overflow of sorts, you might be specifically interested in looking at whenever you call read. So of course the syscall handler within YON85 is kind of going to be where syscalls ultimately come from, as that makes sense, right? This is interpret sys. So some things you really want to look at is exactly how this read memory works, right? Because this read memory syscall, if I can find, why is this? Hold on. Why don't we see it calling read here? Let me switch to this. Wait, maybe we did. Read right here. Okay, yeah, it's buried within this this complex statement. So we can see here that this calls read. So this is definitely, in terms of guiding your analysis in order to kind of figure out what's going on and kind of how you can start abusing things, you want to look at the entry points for data. And so of course the first entry point for data is your instructions themselves. When it calls, where is it? Interpreter loop somewhere, read right here. So this is the first place where you get to influence the program because you're sending it data, right? So you could think that maybe this, when you were sending instructions, maybe you can go out of bounds on how you can basically send enough instructions such that it overwhelms some buffer and allows you to like overwrite something else that's not relevant to this instruction buffer. So it doesn't necessarily have to be that your memory corruption is overflowing a saved instruction pointer. You might be overflowing some data that is extremely useful. So for instance, in this case here of constraints on the program, right? We're only allowed to have one syscall before this interpreter loop happens. And this is, it's going through and it's going through a specific region of how far it's looking for syscall instructions. But you could imagine that maybe you could input more instructions past that buffer. Maybe you can't overflow it saved RIP, but maybe you can have instructions outside of where it's checking for syscall instructions, and then maybe somehow you can jump to that later. I'm not saying that's the case, but this is kind of what you want to think about with memory corruption and buffer overflows. Is it doesn't have to be overflowing saved RIP. It might be overflowing a different part of memory. So you want to look at all of the places that your memory comes in and see if it goes past its kind of logical boundary and enters into a different area that is then later controlled. So that's kind of the thing to think about for 6. Yeah, and then so with 7 though, there isn't necessarily, it's not necessarily abusing even a memory corruption issue. This could be actually something to think about, is that there could be logical bugs that aren't just like memory corruption or heap vulnerability or whatever standard corruption like vulnerabilities. There's logical vulnerabilities, right? There's kind of the idea is that you didn't think of a corner case within what you're doing. And something to think about is how this control flow here, to give a very big hint for 7, is pay attention to the control flow of interpret sys. So we're constrained, right, by this idea that we're only allowed to do one syscall, because this for loop here that counts the number of syscall instructions. If there's more than one, we don't get to interpret our instructions. But something that's interesting is that even with one syscall, how does a syscall get interpreted? It kind of gets interpreted in a very interesting way. So you might be assuming that this control flow, I don't really want to completely go straight into what it is for the sake of letting you find it, but for the sake of honing in what you're looking for here, this control flow is maybe not what you would expect if you were going to write this yourself. So yeah, I guess look at all of the ways that this syscall instruction can be executed. So for instance, you know what happens if the argument that determines the syscall here is a hex 10, and you know if it's hex 20 what it's going to do, and you know if it's 1 what it's going to do, and if it's 2 what it's going to do. But what if it's not one of these values here? I would think about that. All right, if you have more questions about this level, go ahead and message me on Discord or email us or ask in the help channel or whatever. But for now, let's go back to heap, since I'm seeing a lot of questions in Twitch chat about heap. Okay. So let's see what the questions are for heap. Okay, so I see, could you talk about level 11 if possible? I see the stack address and address of main. If we know the offset to win, we could use malloc free as we did in previous levels to jump to that offset. Okay. We know the offset to win. we could just use malloc free as we did in previous levels to jump to that offset. Okay, so the question, I'm not completely understanding this question. Let me start though by launching level 11. Level 11, practice, okay. In the disassembly, there is an offset to win function. Or, okay, so let me SSH in. Are you asking me how to compute the address of win? So when we launch this challenge, right, we can see that we're given 2 leaks. We're given the address of main, which is at this address, and the address of something on the stack, in this case, the address of our allocations. So like when we call malloc 0, 64, or 62, I guess, and then so this is what it's talking about, is this allocations array that there's basically this array on the stack that's keeping track of all of our heap pointers so that they can be used. And it's giving us the address here of that. So basically, if you were to dereference this, you would actually see this address here, if you were to do that in GDB. Okay, so we're given, though, the stack address, and we're given some stack address, and we're also given some main address. And the other thing to realize here is kind of something maybe important to always keep in mind with these challenge. God, I hate that for some reason checksec can't autocomplete. I don't know why that's a checksec thing. But we can see that we have full railroad, the Canary, NX, we've got everything turned on, which is interesting, but fortunately we've been given some leaks. So even though pi is enabled, right, since we're given the address of main, we can compute the address of win. So actually, if we quickly show that there is if we show that there is a win function, which I guess might not be immediately obvious, the fact that there is a win function, something I guess to look out for, is that there is in fact a win function, which is at some relative offset to main. So if we're given this address of main as being this, oops, we can very quickly compute now what the address of win is. So if we do import pwn, elf, and then we can do elf symbols main minus this hex that. Okay, so this is the base of the binary plus elf symbols win. Okay, so you say I know how to compute the offset. Makes sense because we've done this several times in previous levels. I guess I'm still not following then what your question is. Let me try and read it again. No. Oh, you're asking, could we use malloc/free as we did in previous levels to jump to that offset? So in previous levels, before level 11, you've used some combination of, let me launch the level so we can see what we have access to in terms of our menu options. You've used some combination of malloc free and scanf to basically control where the next malloc is going to be. How easily can I show that? Well, I guess we can show that pretty quick. If we do, actually can't, oh God, forgot that that hasn't been patched. If we do import pwn proc equals pwn.process proc dot send line malloc allocation 0 size 64 we've seen in past levels that you can do something that looks roughly like this. Free 0, free 1. So we just set up Tcache now so that there's basically two entries. There's basically two entries within Tcache. But we have the ability to do a use after free on this allocation 1, for instance, or we could do allocation 0, but 1 is kind of next in line for what's going to be allocated. Well, okay, so that's not exactly true. The address that was freed here is next in line, is first going to be. Let me just show it. Clean decode. Okay, so we can see here our allocations. So we know, of course, that if we were to call malloc again, so send line. If we're to call malloc again, that we're going to get this address here because this is what we just freed, so that's what's on Tcache. And sure enough, if we do that, we can see that we got that same address back. Makes sense. Let me just go ahead and free that again. And now again we'd get that. But we've seen in past levels that you can actually scanf onto this and overwrite the address with something else. So we can see here something that we might want to start thinking about. And just I guess as a first for demonstration purposes, we could see, let me read the question. My method was to try and scanf the address of win, but that was unsuccessful. So right here, you said like scanf of win. So what we would be doing if we pass the address of win right now. So if we do scanf onto 3, which is what we just freed, which means that the second thing we get malloc is going to be determined by this address. So if we do send line pwn p64 of, say, this, which maybe is what you're saying, I'm running into is having to have one win be run. Yeah, okay. So maybe what you're saying is that you did something like this, is that you scanf'd over this most recently freed thing so that we can kind of corrupt the forward pointer on that Tcache entry. And then if we just see where we're at, nothing crazy has happened. Now if we do, and hopefully we didn't have any white space characters. I'm not seeing anything that looks like a white space character. Don't think. Hopefully that's not. I don't think it is. Oh wait, but okay. So I guess we'll see either way. If we then did malloc, so let's just do malloc 4. So we will see that the address we get is this is not this address, just to point out, even though they're close, they are not the same thing. D2, and they're like in different parts of the program. So this is still a heap address. We can see that this is the most recently freed thing, but the next thing that we go on to malloc is basically you have to malloc twice after you overwrite, because you're not overwriting the Tcache head pointer, you're overwriting where if you were to do another dereference, basically go to the second element in the linked list is what you're overwriting. So if we were to do one more malloc here, that is where, when we did this overwrite and made it be the win function, that we're going to get our allocation. But we're going to see that we crashed. Yep, we see stopped with exit code -11. So the issue here, and maybe I'm not completely following your question, but maybe this is what you did. The reason that this doesn't work or isn't necessarily a good idea is that this is code, right? This is in the code, the .text part of the program. This is readable and executable only. It is not writable. But when malloc goes and creates this chunk here that it's about to create right here, it has to write some metadata there. it has to write basically, for instance, the size of the chunk so that it can keep track of it for when it goes on later to free it or whatever. And it can't just write there because this is non-writable memory. So just immediately passing the win address here doesn't work, but it also doesn't exactly make sense, right? We're not trying to overwrite the win address, or like we're not trying to overwrite what win does. And if somehow maybe the code was writable, you probably wouldn't want to be overwriting the win function because nothing calls the win function. And maybe you would want to overwrite like partway into main, like where the next instruction that would be executed is. And then you're putting your shellcode there or something. But either way, the code is not writable, so you can't even go down that line of thinking. What you want to do is you want to hijack control flow, right? If you kind of think back to baby ROP or baby mem, control flow is extremely useful to an exploit. And the thing to realize here, and the kind of the concept that we're exploring in this level, is that an arbitrary write is like basically an arbitrary write gives you the ability to turn that into an arbitrary control flow primitive. If you can overwrite the saved instruction pointer on the stack with whatever you want it to be, now you win, right? Or now, I mean, you can make that be the win function is kind of the idea, but you make it be whatever you want for your exploit. Okay, let me keep looking at Twitch chat. Okay, so I'm trying to ask how to modify stack using heap exploit. So we are given a stack address here, or that's not a stack address. I don't know why I highlighted that. Let me leave this. We are given as part of a leak a stack address. And the reason we give this to you is to kind of make this this first exploring the idea that arbitrary write equals arbitrary control flow hijack. And so we give you the address of the stack because once you know the address of the stack, you know the address of saved RIP. And then we also give you the address of main because once you know the address of main, you know the address of win. As you'll see in the next level, we're not so nice giving you these things. You'll have to basically figure out how to get them for yourself. But we do give you an additional vulnerable function that will enable that. But anyways, okay, so the question is how to do that. So if we know where the local stack address of your allocation is at this. Okay, so we want to know, so we've already shown how we can convert main into win, right? Once we know the address of main, we know the address of win. Are you basically asking me how we take the address of allocations and turn that into the address of saved RIP? Is that kind of the question? And I will assume while you answer in Twitch chat that that is the case, and I'll start taking a look at this. Okay, so we're interested in looking at basically what's getting leaked. So we want to see, actually we can see what we want to do. So we see that there is, this gets printed, this gets printed, this gets printed, some more stuff gets printed, and then eventually this gets printed and this gets printed. So we're interested in the disassembly where it is that this gets printed. We're looking for this because this is must be like a printf or something, and this address is getting passed there, so we'll know where it is in reference to RBP. Obj dump. And so then the next, there's also a question in Twitch chat, which is actually a very interesting to think about question. And do we need to leak the canary, or are we just trying to jump past it when we do write? Yeah, so the interesting thing is that canaries only stop or are kind of there in place to stop buffer overflows. But we're not doing a buffer overflow, we're doing an arbitrary write. We have this very or mostly precise, right? You have to think also that as part of our arbitrary right, there is some metadata being written. And if that metadata being written by malloc were to clobber the canary, that wouldn't be great. But it turns out that that's not going to happen here. So yeah, we basically get to skip right over the canary because we're doing an arbitrary write. We're just overwriting saved RIP. We don't have to care about the canary as long as we make sure that the side effects of our arbitrary write aren't corrupting the canary. But they're not. Okay, so this kind of shows that an arbitrary write is extremely powerful because an arbitrary write lets you just skip stuff like canaries. And you could also think that in the case of a stack overflow, that or a buffer overflow, that you might have other useful data on the stack that you're also going to corrupt and maybe cause a seg fault as a result of corrupting, and bad things happen. So an arbitrary write is extremely useful. Okay, so let's look then for, we're kind of looking for a printf, and we're looking for some RBP offsetted thing being put into something that's going to get printf'd. Okay, so this is printf, this is, actually hold on, let me see everything that's being called. Okay, so this puts is probably the first the first line, and then this printf is the thing that says you are running blah 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 program, and then this is puts is another useless thing. This is help information. Then we have a printf here, but this printf doesn't access any RBP offsetted thing. Then we have this printf, which does access an RBP offsetted thing. And then we have another printf, which doesn't use a RBP offsetted thing. We can actually see for this one that objdump is kind enough to resolve this RIP relative thing and tell us that it's actually looking at main. So it seems very likely then that this printf statement is going to be the one that is printing out the address of main for us. And if we remember back, the printf that happened before that is the one actually that printed out our stack address. So we can see that the stack address that is printing out for us is this RBP minus 0x110. So that means if we add hex 110 to our leak, we have the value of RBP. And then if we add 8 more to that, that is the saved RIP. So at plus 118 of our of our leak, we have where saved RIP is. Does that answer your question on kind of what you were asking before? I kind of am guessing that what you're asking is how do we translate that stack address leak that we had into the thing that maybe we care about, which is saved RIP. Okay, so we might want to overflow this, as we were saying. Let's see what that looks like. So we were saying plus 118. Let me just write that down. Okay, so if we go then and import pwn process that, so we need to do 2 mallocs to set up our tcache, and then we also need to do our 2 frees. Okay, so there's another question. Instead of attacking saved RIP, can we change the return address on the stack? What do you mean by that? So saved RIP is the saved return address, right? What is there? Maybe I'm not completely understanding your question. I think you're saying the same thing, right? Saved RIP is the saved return address. Okay, so then as part of setting this up, I thought function return add. Okay, yep. And then we do free, and then we free. Okay, and now we want to overwrite what this most recent freed thing is. Actually, hold on, we should probably do clean so we can see what we're working with. So we said that at plus 118 of this, we will have the address of what am I saying? We will have the address of our saved RIP. So if we take this value and we do plus 118, which we determine this hex 118 statically, which I guess rarely is something that I will do, but it seemed like a opportune time because, I mean, obviously we could just do it dynamically and just kind of basically guess every offset from this, but whatever. Simple enough to do it statically, change up of our reversing strategy. Anyways, we have saved RIP adder equals this. And then we want to compute our win address, which we said is going to be this minus proc elf symbols main. So this will give us the base of our binary in memory. And then we want to add in the offset to win. Okay, so now we have saved RIP adder and we have the win address. So now all we have to do, and also I guess we have our Tcache kind of set up with 2 freed entries. Now what we want to do is do a scanf over 1 because this is our second entry in Tcache that's currently pointing to what this address was, but it's kind of the first thing that we can overwrite because of course we can't overwrite the Tcache head pointer. So we send scanf 1 and then actually something we want to make sure that there's no white space characters. Technically this attack can fail if we have some white space characters in here since we're at the mercy of scanf rather than something more just always works like read. Doesn't look like there's white space characters. Okay, so the first thing that we're going to send is what address we want to overwrite. So when we send, if we do proc send line pwn p64 of saved RIP adder, we are going to be when we do this, we're going to be corrupting basically the second entry in Tcache to be this saved RIP address on the stack. Sorry, how did we get the saved RIP adder? Okay, so we computed it as plus hex 118 away from the leak, this leak. And the reason we know it's 118 is that we statically analyzed to see that this, and you can either rewatch the video or I guess look at objdump yourself, but we can see that when it does this printf here, what it's printing to us is it basically says that this variable here is at RBP minus hex 110, yeah, with objdump. And since this is at RBP minus hex 110, if we add 110, that gives us RBP. If we add another 8, that is where saved RIP is. Because if you don't add the 8, that's where saved RBP is. Anyways, okay. So we want to overwrite saved RIP. So that's kind of the first thing, because once we set up this structure, when we call malloc twice, that second malloc is going to give us an entry here, which basically means now we have something that we can scanf into again, and at that address that would be scanning effing into again would be our saved RIP address. Okay, so if we send this and then we do proc send line malloc to 64, and we want to stick to this 64 since we want to not leave our Tcache bin size. We want to stay consistent on this. We send malloc 2, we send malloc 3, and now if we do a clean, we can see here, very interestingly, rather than our allocation coming to us from the heap, as all previous allocations have been, so we can see C0 and then 1 0 and then 1 0 again because that was the most recently freed thing, but then we overwrote. to give us this address, which is our saved RIP address. So that means that allocation 3 right now is pointing to the stack, which means if we do a scanf on allocation 3, we're writing to the stack, and more importantly, and more specifically, we're writing to saved RIP. So now if we do, you're basically pointing the Tcache directly to the stack and can write whatever we want exactly. So this first scanf is basically corrupting the forward pointer, so that eventually when we call malloc, malloc is going to return that address to us. And now if we can write to that malloc address, and the way we do that again is with scanf, we can overwrite saved RIP. Yeah, so this right here basically means now we've got an allocation pointing at the stack, which is, of course, very useful. So the next thing that we would do is we would proc send line scanf3. So when we do scanf3, we're getting ready to just start writing data to this address. And again, as I keep saying, this address is saved RIP based off of how we statically computed it in addition to the leak. So if we do scanf3, now whatever we send next is going to be what we're overwriting saved RIP with. So if we, and of course what we want to send it is this win address. Let me make sure this looks correct. Yep. Okay, so if we do proc send line pwn p64 of win address, and then proc, let's just do proc clean, print that decoded. We can see nothing's complaining so far. Theoretically, saved RIP is overwritten currently with our win address, assuming everything we've said has been exactly correct. But obviously we haven't executed win yet because we need to leave ret out of main, right? We need to actually leave main. Whereas currently we are in this infinite while loop. And the way that we can leave this infinite while loop is we can send it quit. And when we do quit, we're going to break out of the while loop, and then we're going to leave ret main. And as we leave ret main, our saved RIP address is going to be extremely relevant to where we return to. So now if we do clean again, we can see out comes the flag. So this level basically demonstrates how powerful an arbitrary write is. That given an arbitrary write and some more, of course you need to know where you want to write to, what you want to write, but theoretically you can overflow stack metadata, you can overflow a saved return address if you know where the stack is and if you know where you want to return to, which given both these leaks we can compute what those things are. You can turn a saved, or you can convert a arbitrary write into a control flow hijack. And that is what this level shows. And what the next level will also show is that in addition to, now you basically need to get these leaks yourself, which is important because obviously most programs you're exploiting aren't just going to start printing out their stack address to you. It's not a very common feature. But fortunately, there are use after freeze and all sorts of things that allow you as the person writing the exploits to force the program to leak stuff out to you, as we've seen in all sorts of previous levels. Yeah, programs should start adding just printing out all of their metadata about where their functions are. It'd be very useful. We live in a much securer world, of course. Okay, so let me see what other questions. I've seen 13. Yeah. So yeah, I'm not going to go over 12. 12 will be very similar, but you'll just have to look into the added functionality and how to get those leaks yourself. Okay, so level 13. Level 13 is exploring a new concept. So as we said, when we added these 2 levels, or these 5 levels, where currently we've got 3 of the 5 out. The next 2 will come out at midnight. But this third one, level 13, is going to be similar to 14 and 15 in terms of what the concept is that's explored. And let me launch level 13. Practice. Could you go over 10? Trying to remember what level 10 was. Oh, right. If you watch all the way through my previous office hours, I indirectly discussed the solution for level 10 at some point during it. If we have time, we can go over 10, but let's start on level 13 since this is a new concept. Okay. So level 13. The first thing we want to understand, so I guess we see that we have our 16 allocations that we get to do. But the more important thing is, what are our options? We can see we have some new options here. We've got what is being called stack free, which kind of from its name doesn't necessarily mean much because the stack, you don't call free on the stack, right? You just leave the function frame and the stack pointer clean stuff up, so it's kind of a weird name, but something to do with the stack and being freed. Stack scanf, that maybe makes more sense. We get to presumably write some data to the stack. And we've also got stack malloc win, which with the name win, probably you should be thinking to yourself, at some point we want to call this. Let's see what happens if we call it now. Okay, so we want to win. We can see that in the teaching mode, it's kind of telling us what's happening. So it tells us if malloc of 98 equals this address, and we can see that this is a stack address, or at least it looks like a stack address. Presumably it's some sort of stack address. We win. So it's basically telling us if we can make malloc return a stack address, we win. So we should, maybe the first thing you might be thinking when you see this is we just discussed level 11, and in level 11 we showed that we can make malloc return a stack address. So why can't we just do that again? Well, the first thing to note is that we don't have a leak of where the stack is, so that's probably going to be pretty difficult. But then you might be thinking, well, in 12 it doesn't give us that, and I haven't showed 12, but 12 doesn't give you that leak, and I said you have to get it yourself. But there's a missing function that would allow you to get that leak. So level 12 adds this echo function, which has some vulnerabilities in it that allows you to get a leak. And echo doesn't appear here, so basically we're back to the drawing board of, well, maybe this isn't so easy. How do we get our stack address in order to get a free win? And then it prints maybe some more debugging or potentially useful information, who knows. Basically says malloc usable size of malloc 98 is 104. Okay, maybe that's useful, maybe it's not. As it turns out, this is basically, this value here is randomized for everyone, and it's basically reminding you that bin sizes get rounded up. So if this was like 97, for instance, it would also be 104. And if this was like 99, it would also be 104. Anyways, okay. And then we can see it tells us as well when presumably that's just called malloc 98. And it gave this address, which is not this address. So that probably makes sense why we didn't just get the flag by calling this. Okay, so what we want to do is we want to make this address be the result of malloc. So this is kind of an introductory level to this new concept we're about to explore. So that's kind of why it's just like if malloc returns this, you just get to win. And then the follow-up levels to this will kind of get a little more complicated where it doesn't just do this for you. But we will see that when those come out. Okay, so let's see what our other functions are. So maybe an interesting thing. Let's look at this first one. Stack underscore free. Okay, well, we can already see that we crashed and someone's not happy. That's why we crashed. Looks like Malik is not happy at this operation. But something to note is that we just called free on this address, right? So if this would have somehow succeeded, we could have just then called stack free. If this succeeded, potentially then we could have just called stack Malik win and we would have won. Of course, something to pay attention to, and the idea, I guess, of this level, is that when you go to free something, that there's metadata associated with it. And maybe the most, I don't know, important metadata that's associated with it is the size of it. So if the size was correct for this allocation, we would win. Because if say somehow when it went to free this, it thought that the size was like, I don't know, like 20 or something, and then it freed it, and then it didn't crash, let's say, well, then this still wouldn't work because we're calling Malik 98, and if this was like basically size 20 or something like that, it wouldn't work because we'd go to Malik and this wouldn't give us this address because we didn't call Malik 20, we called Malik 98, so it wouldn't work. Okay, so the idea being explored then in this level is why is this crashing? What's going on? Why can't we free this address? There's clearly must be some important inner workings of free that is detecting invalid pointer or whatever and causing a crash to happen. And we need to figure out how to overcome that. So the other thing that we have access to is this stack scanf, which I guess we can try to see what happens when we do stack scanf. So we can see that it's giving us the ability to write like 127 bytes, and that it's going to this stack address. So let's see what the relation, actually that won't quite tell us because the stack is randomized. Let's do stack Malik win to see this address, and let's do stack scanf to see where we're writing to. So we know that these are two stack addresses. Let's see how they are related to each other. So if we look at this and say like minus this, you can see that they are 64 bytes apart. So that means that as we start scanfing into this address, the first 64 bytes will be, I don't know, some data that we're writing. And then after the 64 bytes, we're actually at this address that's being freed and we get to keep writing. So basically the thing to note is that stack scanf and stack free and stack Malik win are all approximately looking at the same region. Okay, there's a question in Twitch chat. How are those addresses selected for these stack functions? Because the testing version does not leak the stack addresses. Okay, this isn't necessarily an issue though, right? So you can reverse engineer to see maybe if this isn't 64. Spoiler alert, it is 64 still in the testing version. But you don't necessarily care about what these addresses are per se, right? You would only care about exactly where this address is if we needed to write it somewhere. But for this exploit to work, you don't need to write it somewhere. That's not the reason that this scanf is failing. Excuse me, that this free is failing. Okay, so we need to figure out why stack free is failing. Invalid pointer. So let's see here. If we, I'm just trying to think about this problem real quick. Like one, actually no, that's not what we want. Yeah, it's just invalid pointer, invalid pointer. Okay, so something I'm going to kind of look at this from outside of this challenge's perspective, but basically it's still the same idea. If we do, let's go into temp. If we look at and make a test program, if we create some stuff on the stack to kind of simulate what we're looking at. So if we call this, say, data, and let's say we give ourselves 16. So now basically we have 16 unsigned long. Okay. So let's go ahead and say that data 0. Let's just make every single one of these be all A's, just to show that it's just kind of like random data or whatever. 41, 41, 41. Okay. And let's make all of these become 41s. Oops. Okay, so we basically created this structure on the stack, and we've made every single one of the values equal to A's. Just imagine it's some data. Okay, and then let's say we do free of data 8, the address of data 8. Okay. Let's see how this looks on stream. I think it's going to be fine enough. Yep. Okay. Well, let's gcc test.c and then run a.out. Okay, so you can see that there was a segmentation fault. Alright. Actually, why are we seg faulting? Hold on, let's temporarily get rid of those. Okay, so this, we can see, still has basically the same issue that we had before in the actual challenge. It says invalid pointer. What if we make this be 0? I'm trying to figure out why it's seg faulting. Kind of going a little off script here. Oh, something happened here. Okay. So the thing to realize that I'm starting to point in the direction of is what the chunk metadata looks like for an allocation. So if we're going to free this, I'm actually, hold on, let me see if we make that be that. Interesting. If we do that, it seg faults. See, I actually don't know why that's seg faults, but that's okay. Okay, so this question in Twitch chat. So the only metadata has to look right. The chunk can be whatever. Yeah, that's kind of what we're exploring in this level. Okay, so let's say that we free this address here on the stack, right? Hopefully it makes sense kind of what I'm doing here, that this basically looks the same as the challenge. It's just now we don't have to do scanf, so we can just kind of quickly modify what memory looks like. That this can be freed. I don't exactly know why this has to be a 0 or it'll seg fault. I would have thought it would just give this same free invalid pointer thing. apparently not. Okay. Anyways. What happens though, so the thing to realize here is that if we're going to free that address, that right here is size, and right here is like prev size or whatever, theoretically, and more data. So this size, and the reason I keep looking at data 7 instead of data 8, which is the thing we're freeing, is this contains very important metadata for when malloc goes to free. So if we set this to be 0, then it says invalid pointer or whatever. But what happens if we make this be something other than 0? Make it be a valid size. So for instance, let's make it be like hex 30. Let's see what happens here. Nothing happened. Wait, so does that mean we didn't crash? Puts hello world. We did not crash at whatever we just did here. So we can see that 30 suddenly makes this not crash if the previous 8 bytes are, and we can get rid of that. If the previous 8 bytes of where we're freeing at are 30, somehow we are not crashing. That's very interesting. What happens if we make it, say, be 20? Seems like it doesn't care. Hex 10 seems to not be good, so it clearly can't just be arbitrary things. So 30 works. What if we do like 31? Apparently that works. 32, invalid pointer. So clearly we can see that malloc is checking for some specific stuff at the previous 8 bytes, which is what contains the size. And that it is determining basically that you're freeing something that's bad if this is a bad value. So let's stick to this idea of 30 since we saw that that works. So then the thing that we might be wondering is, well, what happens if we call malloc? Yeah. So what happens if we call malloc on, let's say, size 30? And printf percent p that. Okay. So this is a heap address. Fine. So that means that our hopes and dreams of this being like maybe a size 30 thing and then mallocing here for size 30 isn't exactly causing the stack address to come out. And actually maybe it's worth printing out what this stack address is. So let's say that this is like malloc goes here, and then let's say what we're freeing. So let's say that we're freeing here address of data of 8. Okay. So we can see that we are definitely freeing a stack address, but then we're not getting that back. Well, it turns out that this this size here that we write here doesn't exactly correlate with this size here. So if I remember right, I think if we make this be 40, oops, I think if we make this be 40, what we want to happen, no, actually maybe we had to go smaller. Does that make more sense? Maybe that makes more sense. It does make more sense. Okay, so maybe this is just like a random leap into like, oh, look what happens when you do X, but we'll just stick with it. We can see something very, very, very interesting. If we write just to this, apparently we only need to control this. Presumably, even though I wrote A's here, that if it works for A's, probably any value is going to work. It'd be weird if A's are somehow magical. But it seems like if we want to free this address here, all we need to do is make this address here be a valid thing. Or what I mean by that is contain some correct data that's not going to make free crash or complain or whatever. And we see that if we make those 8 bytes be hex 30, so we're kind of overriding this size thing, and we're declaring that it's now 30, and you can't make this completely an arbitrary thing, but there are particular values where free is happy with it, as we saw. And then so we did this to data 7, but then we go on and free data 8. We can see that we actually just made, we freed this address, and then we made malloc actually return that same address we just freed. So we basically just crafted a chunk, called free on it, and now malloc is willing to return it. We basically forged our own chunk. We didn't rely on calling malloc and malloc doing its thing and giving us a chunk and then us corrupting like the forward pointer as we've done a lot in previous levels. In this case, we've just kind of created our own chunk from thin air. And if you guys are wondering, this sort of technique is called, I believe it's called House of Spirit. Let's see here. Let me verify that. How to heap. Let me make sure that I'm not mixing up these insane names. Yeah, this is called House of Spirit. And House of Spirit has to do with basically creating this fake chunk. Okay, so if you put data 8, it should return all A's correct. Let's see if that is the case. So let's call this car A equals that. And then let's change that. And then let's call puts on A. Why do I keep hitting that? Okay. And then we run it. It's not doing that as we'd hoped. Let's see. Why not? So I would expect that if we did like plus 16, it would work. Yeah, we can see that if we do plus 16, it works. In fact, let me make this be 0, 0, just so it kind of terminates eventually. Why is that? Yeah. Let's see if 8 works real quick. Actually, yeah, let's see. 8 does not work either. So presumably it's like zeroing out. You'd have to look into the exact mechanisms of how the heap is working here. And to be completely honest, I don't fully know exactly how this works. I'd have to look into it as well. I guess this sort of implies that, oh no, it's probably the free. Oh, interesting. Okay, so what I would expect actually is that free is writing the metadata here. So when it calls free, we have a forward pointer that needs to exist, right? And we have a key that needs to exist. So if we do, yeah, we can leave that in, why not? If after this free, if we do printf, how can I show this easily? %x, maybe something like that. And then let's do data of 8. And let's call this data of 8 equals that. So we can see that this equals 0. So, and actually if we, hold on, let me also include 9 and 10. Oops. Yeah, it's very interesting to see the exact mechanisms of how these things work, and it's very important to investigate and explore these things. Okay, so we can see that 10 didn't get corrupted. And real quick, just for more clarity's sake, actually we'll do it before this statement. We can print out this. Okay. So we can see that before we call free, that all of our A's are still there. Makes sense. Nothing's changed on that front. But then we can see that once we call free, that these things, that 8 and 9 get modified. And if you remember back when you call free, so I think I do have the answer actually for why this happens, is that when you call free, this is now going into the Tcache linked list structure. So that means that now at the head of Tcache for this particular size is this address here, which makes sense. And then in order to maintain this linked list, it's basically saying that the next thing is nothing, because what was previously there was a null pointer, and now we've overwritten the forward pointer to also be a null pointer. And then the other thing is the key, and the key, as we know, is this kind of like heap address that prevents double frees and stuff. And so that also gets written on the free, so that when we eventually call puts on A, it doesn't actually give us our A's because they have been overwritten by free. Hopefully that makes more sense. Yeah. So what else is there to explain with this? Okay, so I was doing some testing to understand how the sizes work, and for everyone's benefit to not have to go through the sort of same torturous process, let me also explain how this size thing works. So if you're going to call malloc, actually, it's kind of interesting. Huh. I just realized I didn't call malloc at the start. I don't know why we didn't have to do that. So in the Shellfish's how to heap thing, they basically do a malloc 1 at the start, just for the sake of doing it, and they kind of like say that this is getting like Tcache ready to go or something. I have no idea what that means. And we just saw here that that didn't actually matter. So I don't really know what the deal is. Maybe it's because these printfs under the hood are calling it for us. Hold on, if we comment all of our printfs out, just get rid of everything except the bare minimum to make sure we only call malloc here. We get rid of that as well. This doesn't crash, does it? No, it doesn't crash. Yeah, I don't know. For some reason, if you look at the how to heap on Shellfish's thing, they kind of do this malloc at the start and they say it's getting Tcache ready. I don't know. Maybe this is needed in some cases and not in others. We just clearly saw that it's not needed for our case, which is interesting. I don't know exactly why theirs was needed. Anyways, so the other thing I was going to point out is that we can see here we're mallocing hex 20. Well, we can malloc, of course, any size, right? When we call malloc, the size isn't like super constrained on what the valid values are. And we can see that even shifting 20 to 21, right, it still works. I've determined that the way to compute this address, not this address, but what this value here needs to be, is that we can do the following. So if we're going to malloc, say, random size, like 71, and then we can call malloc get usable size, which is why in level 13 you see that I print that out for you, just to be slightly helpful there. Let's say usable Actually, instead of %x, let's do %d. And no, let's do %x. It's cooler. All right. What did we not get? Who's complaining? Undefined reference to malloc get usable. Okay, that's not exactly that, is it? No get malloc usable size. That's probably correct. Okay, so we can see that when we did hex 71, that malloc usable size is hex 78. Should probably %p just 0x it, or yeah, okay, sweet. We can see that when we print out the usable size for some malloc of 71, that it is hex 78. So let's actually go ahead and make this be the same thing for what I'm kind of trying to show here. We can see, where is it? So we're no longer getting our stack address, which makes sense because we're not changing data 7 to be the right thing here. So we're no longer doing that. But what we can do is what I've found, and it's worked in every test I've done, I'm pretty sure this is accurate, is that if we take whatever the result is of this malloc usable size, malloc hex 71, and we saw that that returns hex 78, if we just do this plus 8, I know it's kind of weird or whatever, but that plus 8 seems to do the trick. If you don't do plus 8, we are probably going to crash. Yep, invalid size. But if you do this malloc usable size, and actually something maybe we want to take a quick look at is just for further exploration of what's going on. It's kind of useful in dealing with new things to either A, read the source code of libc, which is very useful as well, B, look up documentation, but C, a very useful thing to do is kind of do what I'm doing here, which is just kind of explore around in a C program and see what's going on in memory. You could also, of course, do GDB, but I think it's a little easier to just write C and see what's happening. Okay, so what I'm curious about here is if we make this be, let's call this an unsigned long, let's look at what the previous 8 bytes are of this. So this is B, and then I'm curious about is what is the value of B -1? I think that'll work. We probably don't want to call this, or let's call this size, because that should be where size is stored when we malloc something. Is that the same value? It's not. Hex 71? Or hex 81, I mean? Well, that's weird. Actually, maybe, is that weird? Yeah, that seems kind of weird. Okay, hold on. If we malloc 72 then, does it go up by 1? No, that also calls it hex 81. I think it's storing some metadata here. Yeah, okay, here's what's going on, I think. Actually, hold on, let me quickly look at Twitch chat. So would we repeat this process here on our challenges and see what size values don't fail? So you can either do it that way, or as I said, if you do malloc get usable size on an allocation that's the size. So for instance, if in the challenge it's going to do malloc 71, in the teaching it tells you what the malloc usable size is of that value. If you add 8 to it, it'll work. It's kind of the moral of the story. If you can't quite get that to work, yeah, just kind of experiment with some things, but that will work. So I'm interested here is, I'm kind of curious, I mean, the correct way to figure this out would be to look at the source code for malloc usable size and see what it's doing. But what I'm guessing it's doing is it's subtracting 8 and getting rid of some flags. So what do I mean by that? So we can see that in 71, this like previous value is hex 81, even though we did this, but it's not related to this one part doesn't matter, I think is what we determined. If we do like 73, we see that it's still 81. So I think what's happening here is that the size it's going to is hex 80. Actually, hold on, let's see what happens here if we do 80. No, that doesn't quite work. I don't exactly know. But what I'm pretty confident of, is that the last 3 bits of this size here aren't actually the size. So a size has to be some multiple of what is it, 16? Does that sound right? Yeah, 16. Because the 3 least significant bits, and I think Jan talks about this in his lectures, I'm pretty sure, is that there's 3 bits here. And actually, if we, let me pull them up real quick. If we like, so another like useful resource that I'm not going to show on stream because I don't want to make OBS figure that out, is there's this thing called like the Ctf Wiki, which is increasingly becoming more and more useful as time goes on. And if you just like Google for Ctf Wiki heap Tcache or something, that's what I just looked for. There's this Tcache, like discusses a whole bunch of stuff about Tcache. Let me find the relevant part I'm looking for and just paste it into Emacs. Actually, maybe it's not. Maybe it's not in the Tcache section. Maybe it's just in the heap section. Heap overview is what it's called on this Ctf Wiki thing. What am I looking for? There's like these where is it? Like flags in use. Map. Where are the flags? It's like there's like a prev in use flag. Heap structure. Maybe this is the thing. Okay. There is, how do I make this be clearer? Oh, maybe this is the thing to copy. Okay. Yeah, let's just copy this. Not what I wanted to copy. This. Okay. So we can see that what we were talking about before, and here I'll actually just paste it in Twitch chat for anyone curious, but if people are watching YouTube video, if you Google for Ctf Wiki heap structure, that is what it will be. Anyways, and Jan talked about this in his slides anyways, there's these 3 flags here that I think is what we're seeing when we see this hex 81. And I think it's just this flag that Tcache uses, I think. So what the flags are, let's see here. So this first one, this A, according to the Ctf Wiki, they're calling it the non-main arena. It basically says whether or not the current chunk belongs to the main thread. So I think this is just basically always going to be 0, or at least in certainly in our case where, oh yeah, actually, because Tcache is per thread, so it probably will always be 0 for Tcache. This M says basically whether or not it was allocated by mmap, and since we're doing Tcache, I think that should also always be 0, because we're not doing mmap chunks, pretty sure on that. And then this basically states whether or not the previous chunk is allocated. And I think I haven't completely confirmed this, so I'm gonna kind of make something up, and maybe it's correct, maybe it's not. It's definitely worth investigating if you actually want to know the truth on this rather than just take my word for it. Is I think that this thing is always 1 for Tcache because it marks whether or not the previous chunk is in use. And I think Tcache only supports up to like 7 entries. And my guess is that in order for Tcache to be as fast as possible, it never wants to consolidate Tcache chunks. So I'm guessing it just flags this prev in use thing as always being 1, so that the heap implementation never tries to consolidate them and waste time, because Tcache wants to be as fast as possible. And since you can only support like 7 small-ish chunks, at least in 1 bit, it's a relatively small amount of memory that can go into all of Tcache. I don't think they care about consolidating chunks. I think they're fine with Tcache being a little like fragmented, is my guess. And I think that's probably why this flag is always 1 for Tcache, so that it doesn't try to consolidate. I don't know. That's kind of my guess. Anyways, I think we've kind of covered now what it looks like to craft a Tcache chunk. Are there any more questions? I'm just going to, oh, I've got one question. Okay, great. Go for it. So when you did puts data of 8 plus 16, which was, I think you're talking about when I did that here. Yep. You are essentially putting data 10. I believe that is true. So all of these should be equivalent. If I do, you're calling it data 8 plus 16, and also data 10. These should all be equivalent, or not. That I think we need an adder of. Actually, probably for both of these. Don't know what happened here. Hold on. So this one worked. Is it because, oh, is it because we're in unsigned long, the compiler is doing a size of thing? Hold on, that's not where I wanted my parentheses. Let me see if this works. I think this is like an operator. No, this is, okay. Then if we do, instead, if we just make this be an unsigned long cast, I think then it will be equivalent, yeah. So the reason it wasn't working without this cast is that I guess when we do the address of this data of 8 address of, it knows that this is still the compiler is treating this as an unsigned long pointer, and then it's doing pointer arithmetic. So in fact, actually I can show what that means. If we do +2, it will work. If we cast it unsigned long, it will work. And then basically what the equivalent is of this is +2. This like 2 has this implicit times size of, I think size of unsigned long. I don't think it's a long pointer. I think it's the size of, yeah, I'm pretty sure this is right. This is what the compiler is doing under the hood. Yeah. So there's all sorts of C/pointer arithmetic, how it all translates. Yeah, okay, so these are all equivalent. And maybe this is not so easy to see, but yeah. Okay. Any more questions? Hopefully this explanation of crafting your own chunk is useful. I think you should be able to directly apply what I've just talked about here to solving level 13. And then levels 14 and 15 will follow this same principle, but with a little bit of extra stuff. Okay, so someone asked, and we'll go over it real quick. Hopefully real quick. Any hints on 10? Actually, yeah, we'll keep it brief with the following. Actually, hold on, there's another question. For crafting chunks, we don't need to malloc the data array. No, so the reason this works this way, the reason I'm discussing it in terms of like having this stack thing and like modifying data on the stack and then freeing this thing on the stack, is that in the case of level 13, we have these stack free, stack scanf, stack malloc win that basically all correspond to that exact same structure. Yeah. That basically when you're scanfing, you're able to do this sort of thing where you're changing the layout of the data, and then when you do stack free, it's basically just doing this. And then when you do stack win, it's basically just doing this and seeing if it's the correct address and calling win if it does have this correct address. So this should translate like basically almost entirely directly to level 13. Hopefully you'll find level 13 easy with this information. Okay, but anyways, any hints on 10? Yeah, so the hints I would give for 10, that I think most people probably get caught up on, is that with 10, if you allocate a, if you do a malloc, and malloc returns an address that's basically on the BSS in like a very confined, constrained way. And the reason you want to make malloc return that is so that you can, like, for instance, overwrite data on the BSS in order to later get the flag, of course. So I guess what I was saying is if you malloc and you end up with an address on the BSS, what it's going to do is it's going to discard that. But the thing to realize is that malloc still just happened. Like, the program's not aborting or terminating or something. The allocation happened, but you don't have a reference to it. But Tcache just updated. The linked list structure just popped that address off of the head, dereferenced it, and moved that to be the new head. If you think about it from the perspective of, well, what if we're trying to malloc at where the secret is? Well, now the first 8 bytes of the secret are sitting at Tcache head as a pointer. And if you did malloc again, you'd segfault because that's not a valid address. But what if your next operation isn't malloc? You don't want to segfault. But there's important implications to the fact that the secret is sitting at the Tcache head. How can you move that data, which is sitting there, to a different address that you can then access? There's actually a clever way that you can, and this is what level 10 explores, so you can basically do an 8-byte mem copy, which is really cool. So yeah, I guess the hint is push past your allocation being discarded. I know it's like, it's scary, your allocation just got deleted, but you're not done yet. You can keep going. There's more to do. Tcache is still in play. Yeah, so kind of figure out what's next. Okay. Any last questions? Otherwise, I'm going to wrap up office hours. All right, I will take that as a no. If you have more questions, feel free to email us, or ask me the question either on Discord or in the help channel, because I'm going to wrap up this office hours. Yeah, about like toddler 5. Ask any questions in the help channel, ideally, or if it's very specific to something that doesn't belong in the help channel because it's like your code or whatever, send me a message on Discord or send us an email. Otherwise, yeah, I'm going to wrap up these office hours. All right. Goodbye, everyone.